Hello students, welcome to chemistry class. So after a long gap, we are going to meet again. So I'm really happy. So today we are going to discuss about thermodynamics. So here in class 11, so we have almost discussed most of the parts in thermodynamics. Today we are going to discuss about relationship between Cp and Cv for an ideal gas. So already we studied about what is Cv and what is Cp. The Cp formula is dou H by dou T at constant pressure, and Cv equal dou U by dou T at constant volume. So this is the formula we already studied. Now from the definition of enthalpy, from the definition of enthalpy, H equal U plus PV. H is enthalpy. Okay. Then U, as usual, you know that that is internal energy. Then P is pressure. Then V is volume. Okay. Now, for 1 mole of an ideal gas, for 1 mole, keep equation 1 of an ideal gas, we know that you already learned in that gaseous state topic, PV is equal to nRT. Okay. So you are going to substitute this value here. So keep equation 2. Okay. So substitute 2 in equation 1. So we will get H equal internal energy U plus nRT. Okay. This keep equation 3. Now you are going to differentiate the equation with respect to temperature. So differentiate with respect to temperature. We will get dou H. You are going to differentiate equation 3. Okay. So dou H by dou T equal dou U by dou T plus nR, that is constant, then remaining dou T by dou T. Right. Now we know that dou H by dou T, that is Cp, we already discussed in the first step. See here. So Cp equal to dou H by dou T and Cv equal to dou U by dou T. So we are going to substitute these values here. Okay. So dou H by dou T, that is Cp, equal, and dou U by dou T, that is Cv, plus the remaining nR, because this 2 will be cancelled. Right. Now I am going to keep this nR one side and this take this Cv another side. So what will happen? Cp minus Cv, you will get nR. So this is the relationship between Cp and Cv. So Cp minus Cv equal to nR. This is equation 4. Okay. So here actually the Cp is always greater than Cv. right? So these are the relationship. So for that you should know at a constant pressure processes generally, so at a constant pressure processes, a system has to do work against the surrounding. So a system, for example, this is the system, okay? This system has to do work against the surrounding. This is the surrounding. This is surrounding and this is the system. So when the system work against surrounding at constant pressure processes, so it has to raise its temperature normally. So it requires more heat to affect a given temperature rise than at constant volume. So that Cp is always greater than Cv. Clear? Okay, fine. So now we are going to learn about the calculation of delta U and delta H. So for 1 mole of an ideal gas, so for 1 mole of an ideal gas, we know that Cv is equal to, so we already learned about dou U by dou T, but here we are going to write du by dt. Both are same, okay? Du by dt. So we can write du equal, sorry, it's a capital letter, du equal Cv into dt, okay? So for finite change means there is some limited changes. So infinite, finite. So infinite means there is unlimited change. Finite means only limited change. So for finite change, we have delta U equal Cv delta T. So we are changing this D into delta, right? So delta U equal, we can write Cv into, instead of this delta T, there is a difference, temperature difference, T2 minus T1, okay? So finally, now we are going to write for n number of moles. For n moles of, so this all for 1 moles. Now we are going to write for n number of moles of an ideal gas, delta U equal, we are going to multiply by n number of moles Cv into T2 minus T1, okay? So this equation keep 1. Similarly, for an n moles of an ideal gas, so here we are changing delta H. So delta H is equal to, it will come n Cp T2 minus T1, okay? Because the relationship Cp is always dou H by dou T, okay? So when we got against the Cv, delta U is equal to n Cv. So if we change delta H, we are getting here Cp. This is equation 2. Clear? So that's all about the calculation of delta H and delta U. So if you want to calculate delta U, this is the formula, and if you want to calculate delta H, this is the formula, right? So now one problem, that question is related to your delta U and delta H calculations. So calculate the value of delta U and delta H on heating. So you are going to take oxygen. What is the weight of oxygen? That is 128 gram of 128.0 gram of oxygen, and you are going to heat from 0 degrees Celsius to 100 degrees Celsius. Now Cv and Cp values are on average are 21 and 29 joule mole power minus 1, Kelvin power minus 1 respectively. So the value of Cv is 21, value of Cp is 29. So Cv value is 21 and Cp value is 29. So we know the formula for delta U equal N Cv T2 minus T1, and delta H value is N into Cp T2 minus T1. Now here we have to calculate the number of moles, that is N. How to calculate the number of moles? The mass is given. So mass divided by molar mass of oxygen. Okay. So mass is 128 gram. Molar mass of oxygen, there are two oxygen atoms. One oxygen 16 plus 16 equal 128 by 32. So we will get N value, that is 4. The number of moles are 4. Okay. So now we will substitute all the values here, then we will get the answer. So now the temperature T2 is 100 degrees Celsius and T1 is 0 degrees Celsius, because we are raising the temperature from 0 degrees Celsius to 100 degrees Celsius. So T1 is initial 0 degree and T2 is 100 degrees Celsius. So T2, that is, you are going to convert into Kelvin. So 100 degrees Celsius, 100 plus 273, we are getting 373 Kelvin, because all the value must be in Kelvin. Temperature 1, that is 0 degrees Celsius, converting into Kelvin, 273 Kelvin. So now substitute all the values in the formula. Delta U formula is delta U equal N Cv into T2 minus T1. N is number of moles 4 and Cv value, that is 21, into T2 is 373 and T1 is 273. Now 4 into 21 into 100, so finally we are getting 8400 joules. So convert into kilojoules, because 1000 joules equal 1 kilojoule. Okay, so 8400 joules, we are getting 8.4 kilojoules. So that's all about delta U. Now convert into delta H. So calculation of delta H. So delta H equal to N Cp T2 minus T1. N value is number 4 into Cp value 29. T2 is 373 minus 273. 4 into 29 into 100. So 11,600 joules. You know 1000 joules are equal to 1 kilojoules. So convert into kilojoules. Delta H value is equal to 11.6 kilojoules. So that's all about delta U and delta H calculations. Similarly, one evaluate yourself question is given, that is question number 2. Make it as the homework. So work out and upload in the flip plan. So I will check and evaluate it. So this question similar to this problem 7.3, you refer and complete. In case if you have any doubt, please contact me. Okay. So next we are going to study about the measurement of delta U, that is measurement of delta U and delta H using calorimetry. Okay. Now we studied the calculations of delta U and delta H. Now we are going to measure this delta U and delta H using calorimetry. So there are two types of calorimetries are there. One is bomb calorimeter, another one is coffee. So now we are going to learn about the measurement of delta U and delta H using calorimetry. See, calorimeter, it is used for measuring the amount of heat change in a chemical or physical change. Okay. So generally this calorimeter is mainly used to check, to calculate, to measure the amount of heat change in a physical or a chemical change. Then in calorimetry, the temperature change in the process is measured, which is directly proportional to the heat capacity. So each calorimeter has its own heat capacity, and also by using the expression C equal to Q by M delta T. So we can easily calculate the amount of heat change in this process. So calorimetric measurements are made under two conditions. One is at constant volume QV and another one is constant pressure. So first one, we are going to check the delta U measurements. Okay. So for a chemical reactions, heat evolved at constant volume is measured in bomb calorimeter. So this delta U we are measuring by using this bomb calorimeter. Okay. So this is bomb calorimeter. So here, see, this is the picture. This is bomb calorimeter. See, it contains the inner vessel that is called bomb. So this is the first point. Actually, you have to write all the points. So the inner vessel, the bomb, and its cover are made of strong steel. Okay. So see here. So this is bomb. Okay. So this box is called bomb. So this is made of, it is covered with strong steel. Okay. So this is bomb, and inside a crucible is there. So this is the crucible. Inside the crucible we are keeping the sample. Now I will explain one by one. So first point, the inner vessel and its cover are made of strong steel. Then second point, this is point number 1. And second point, the cover is fitted tightly to the vessel by means of metal lid and screws. So that bomb, the cover is fitted tightly and the vessel by means of metal lid and screws. Then you see third point. So actually this is bomb calorimeter, and a weighed amount of substance is taken in a platinum cup. So a weighed amount of substance is taken in a platinum cup connected with electrical wires for striking an arc instantly to kindle combustions. Kindle combustion means like to take the fire quickly. Okay, so this heat is done by that, burning is done by the electrical wires. See here, these are the electrical wires. Okay, so when that electrical wire is connected to the current, here you will get the spark. Also here this oxygen is supplied inside the bomb. So what happened, there will be a lot of fire, so this substance can burn easily. Okay, so the bomb is then tightly closed. The bomb is then tightly closed and pressurized with excess of oxygen. The bomb is immersed in the water. See here, so this blue color, this part is full of water. Okay, this blue color is full of water. So this bomb is completely immersed in the water. So the bomb is immersed in the water in the inner volume of the calorimeter. So that calorimeter contains full of water. Okay, so inside that water, that bomb is placed. A stirrer is placed in the space between the wall of the calorimeter and the bomb so that water can be stirred uniformly. See the picture. So this is the stirrer. Okay, it contains like a small fan, so it can uniformly spread the water, spread the temperature and spread the water also. So this is placed between this bomb and the wall of the calorimeter. Okay, so the reaction is started by striking the substance through electrical heating. When you switch on, there will be a fire in that crucible where that substance is placed. So that is done by the electrical heating. Then next, a known amount of the substance is burnt in oxygen in the bomb. So before placing that substance, you have to weigh that substance, then place it. Heat is evolved during the reaction and is absorbed by the calorimeter as well as the water in which the bomb is immersed. So the heat is evolved during the reaction. It is absorbed by the calorimeter as well as the water. Both that bomb as well as the water, both will absorb. The change in temperature is measured. So this is the thermometer. Here we can see the changes. Is measured using Beckman thermometer. Since the bomb is sealed, its volume does not change and hence heat measurement is equal to the heat of combustion at constant volume, delta U C. See here, that bomb is sealed, so that see here that volume does not change. Volume is constant. There is no change in the volume. So from initial to final reactions. So that it is equal to heat of combustion at constant volume, delta U C. So next you see the amount of heat produced in the reaction delta U C at constant volume is equal to the sum of heat absorbed by the calorimeter of water. So that formula is heat absorbed by the calorimeter. So we have to calculate for both. First one is by calorimeter and second one is by water. Now we are checking by the calorimeter. Q1 is equal to Q1 is equal to K into delta T. Here K is the calorimeter constant. K is the calorimeter constant. It is equal to MC Cc. MC is mass of calorimeter. MC is mass of calorimeter and Cc is the heat capacity of calorimeter. Okay, Cc is heat capacity of calorimeter, that is the constant value. MC is the mass of the calorimeter. Okay, so K is the calorimeter constant. It is equal to MC Cc. Now second we are going to check by the water absorbed by, the heat is absorbed by water, that is Q2 equal MW Cw delta T. Here where M is the molar mass of water and Cw is the molar heat capacity of the water. Molar heat capacity 4184 kilojoule Kelvin power minus 1 mole power minus 1. Okay. So therefore, this is heat absorbed by calorimeter and Q2 is heat absorbed by water. So we have to add both. So delta U C equal to Q1 plus Q2. Substitute the value K dot delta T plus MW Cw delta T. Now delta T is common, here also common, so take common. So delta T in bracket K plus MW Cw delta T. So this is the final formula. Now calorimeter, see here, calorimeter constant. So that calorimeter constant K, that value is determined by burning a known mass of standard sample, that is benzoic acid is the standard sample we are burning, for which the heat of combustion is known, that is minus 3227 kilojoule mole power minus 1. So this is calorimeter constant. We are calculating, we are determining by burning the known mass of standard sample, that is benzoic acid. Then that enthalpy of combustion at constant pressure, the enthalpy of combustion at constant pressure of the substance is calculated from the equation. So this is the equation. That is delta Hc pressure equal to delta U 0C at constant volume plus delta Ng RT. Okay, so that's all about bomb calorimeter. Okay, now we are going to study about the applications of bomb calorimeter. Now they see the applications of bomb calorimeter. First application, bomb calorimeter is used to determine the amount of heat released in the combustion reaction. So when the question comes, you have to write these three uses. Suppose if the question come explain about bomb calorimeter, you no need to write these applications. If the question asked about applications, then only you should add this 3 point. Otherwise, maybe sometimes 3 more questions comes like applications of bomb calorimeter, then you write this 3 point only. Okay, second use, it is used to determine the calorific value of food. So we can check the calorific value of food. Then third use, bomb calorimeter, it is used in many industries such as metabolic study, food processing, explosive testing, etc. So these are the 3 important applications.
Major parts of a bomb calorimeter are an outer copper shell called calorimeter and the inner shell made of stainless steel where the fuel burns called bomb. 2 fuse wires made of magnesium fixed to a 6-volt battery are used to ignite the fuel. A channel for the supply of oxygen is placed to help the burning of fuel. The steel shell or the bomb is enclosed inside the copper calorimeter. The calorimeter is closed from top using a copper lid. The space between the calorimeter and the bomb is filled with water. A mechanical stirrer is placed and on the opposite side of the stirrer, a thermometer is installed. The calorimeter is enclosed inside a capsule with an air jacket between the inner shell and the calorimeter and a water jacket between the inner and outer shells. During the process, fuel of a known quantity is placed inside the bomb and ignited. The bomb is filled with excess oxygen at 25 to 30 atmospheric pressure. The heat generated in the process is dissipated to water present in the calorimeter chamber. The mechanical stirrer is used to maintain a uniform temperature of the water. The amount of temperature rise in the water is noted using the Beckman thermometer.
So next one is delta H measurements. So there are 2 types of measurements of delta U and delta H. One is by bomb calorimeter. So delta U, it is measured by bomb calorimeter, and delta H, it is measured by coffee cup calorimeter. Okay, so this is the picture of coffee cup calorimeter. See, it's like a just like a cup. Okay, like a thermocol cup. So delta H measurements. So here you start from here. So here heat change at a constant pressure, that means at atmospheric pressure, can be measured using a coffee cup calorimeter. So a representation of coffee cup calorimeter is given in figure 7.7. This no need to write. Leave it this point. Instead of bomb, a styrofoam. So it's like a plastic cup. Okay, styrofoam cup is used in this calorimeter. So start from here. Instead of bomb, a styrofoam cup is used in this calorimeter. Then it acts as good adiabatic valve and does not allow transfer of heat produced during the reaction to its surrounding. So heat will not transfer to the surrounding. So this entire heat energy is absorbed by the water inside the cup. So here also water is there. So that entire heat will be absorbed by the water placed in the cup, styrofoam cup. This method can be used for the reaction where there is no appreciable change in volume. Okay, so the change in temperature of water is measured and used to calculate the amount of heat that has been absorbed or evolved in the reaction using the following expressions. So that formula is Q equal mW Cw delta T. So where m is the molar mass of water and Cw is the molar heat capacity of water. The value of molar heat capacity, that is 4184 kilojoules Kelvin power minus 1 mole power minus 1. See here. So this is the coffee cup calorimeter. So this is the water. Inside water, you can see. Then this is here you can place the sample, and this is thermometer. This is the reaction mixture. So once the reaction started, that heat is absorbed in the water and finally it will be calculated by using the formula. So that's all about the measurement of delta U and delta H. Okay. So next we will see one problem. Then after that we can wind up. So now see the question. It is problem 7.4 in your textbook. So calculate the enthalpy of combustion of ethylene at 300 Kelvin at a constant pressure. If its heat of combustion at constant volume delta U is minus 1406 kilojoule. Okay, so in that bomb calorimeter we studied delta H constant pressure equal delta U volume plus delta Ng RT. Okay, so this formula we can use. So we are going to calculate this delta H. Okay, so delta U value, that is minus 1406 kilojoule, it is given, and delta Ng, that is the difference between the number of moles of product minus number of moles of product minus number of moles of reactants. So this is product, this is reactant, but it should be in gaseous conditions. So wherever the gas, then only you have to take the gas only. Don't take other states. You should not consider solid, and liquid should not be considered. Only gas should be considered. So C2H4, this is ethylene plus oxygen. So combustion means it reacts with oxygen. So ethylene plus oxygen, we are getting carbon dioxide gas plus water liquid. So don't count this water because it is in liquid state. So number of moles in the product, only this carbon dioxide we have to consider. So 2 minus, here both are in reactant, total number of moles 3 plus 1. So total 4 equal to minus 4. Sorry, minus 2. Now substitute in the formula delta H equal delta U plus delta Ng RT. So delta H equal minus 1406 plus the value of delta Ng, that is minus 2, into RT, R, that is R value is 8.314. This is constant, gaseous constant. So substitute 8.314 into 10 power minus 3. Okay, into 10 power minus 3 into, then temperature value, that is 300. It is given in the question. So finally we will get the answer minus 410.9 kilojoules. So use the calculator or work out, use the logbook and find out, you will get the answer. Okay, so one more evaluate yourself question is there. Evaluate yourself. Question number 3 is the homework. So work out and refer this problem number 7.4, then upload in the flip plan. So I will check. Okay students, hope you understood the lesson well. In case if you have doubt, so you can contact me. So thank you very much.